In this video, we're going to study how the wave we just observed in Maxwell's equation propagates in free space. To talk about how our newfound waves propagate, we need to discuss power flow. Power flow for electromagnetic waves is described by the pointing vector S, which I've always found hilarious because it points in the direction of power flow, even though it's not spelled that way. We're skipping the derivation of the pointing vector because it's pretty involved. But the upshot is that the instantaneous power flow is equal to the cross product of the E and H fields. That means the direction of power flow is normal to both E and H because it's given by the curl between them. As usual, we care about the time averaged power more than instantaneous power. Fortunately, we can use our handy analytical representation to quickly calculate time averaged power flow, just like we did with voltage and current. We need to figure out what these waves look like, and for now we're going to be doing so in free space. So I've copied down our wave equation, and a reminder that in free space mu is mu naught and epsilon is epsilon naught. The first simplification we're going to make is to assume our wave is one-dimensional. That makes calculations much easier. It also means we're assuming that our waves are planes where there's no variation in y or z directions. That looks like this. We call this type of 1D wave a plane wave because each moment in time is represented by an entire 2D plane. Next, we're going to presume there's some sinusoidal boundary condition that creates a wave that's oriented in the z-hat direction. You can see our familiar k omega minus omega t, kx minus omega t formulation inside the wave, indicating that this is a valid solution to the wave equation. The choice of having our wave point in the z-hat direction might seem weird, and that's because it's a bit arbitrary. We're not letting our E wave point in the direction of propagation because that seems odd, though it's not impossible. We'll see more about that later. And if E isn't pointing in the x-hat direction, then we can pick any other direction in the plane arbitrarily because everything is rotationally symmetric for now. So we choose z-hat because it'll make our math easier later. As a vocabulary note, this z-hat coefficient that specifies which way our field is pointing is referred to as a polarization. Our waves are polarized in the z-hat direction. One question we might have is how E and H are related when they propagate. We're going to find that out by using candidate solutions for E and H. I've copied our E plane wave from an earlier slide, and our H plane wave turns out to be the same form if we chase Maxwell's equations through to find a wave equation for H instead of E. We're going to assume H points in the y-hat direction for now, which is kind of a bold assumption. However, if it turns out to be right, we'll have learned something important about E and H waves, specifically that they're always normal to one another. We pick a Maxwell's equation to compare these two candidate solutions. We need one with both E and H in it, and this'll do. We figure out the left-hand side by remembering our formula for curl after some frantic diving through old notes. The formula turns out to be pretty long. However, it's easy to evaluate because we only have a z component to our E field, and our E field only varies in x, which means only the dEy dx derivative produces any quantity. The result points in the y-hat direction. Next, we take the derivative of our candidate H solution to figure out the right-hand side of Maxwell's equation. The result points in the y-hat direction still because time derivatives don't affect spatial orientation, which lines up with the direction we calculated in the curl of E. That means our choice of pointing the H field in the y-hat direction was correct, because it makes the Maxwell's equation self-consistent. So we know that our E field is normal to our H field because of the curl operators in Maxwell's equation. Finally, we can put the results of the past two lines back into Maxwell's equation and rearrange to find the ratio of E plus to H plus, which are the coefficients for our candidate solutions. The result is a constant that's pretty close to 377 ohms, which means our E and our H fields are always in phase, but scaled versions of one another. The amount they're scaled by, this 377 ohm quantity, is called the impedance of free space. And you'll notice that it does have units of ohms. Finally, one last bit of terminology. E and H both point in the z hat and y hat directions, which are both normal to the direction of propagation x hat. This is a special condition, so this type of wave gets a special name, a transverse electromagnetic, or TEM wave. So in summary, we defined a quantity S, the pointing vector, which specifies the power flow, and noted that we can calculate our average power flow using an analytical representation of E and H, and that it is calculated as the cross product between those vectors. We observed that E is normal to H, and that both of them are normal to S. We noted that E and H are in phase, and they're scaled by 377 ohms, the impedance of free space. And finally, that if both E and H are normal to propagation, we have a special type of wave called a transverse electromagnetic wave.